Good morning, Vinod.
Hello, good morning.
Oh, welcome.
Thank you.
We are waiting for the participants to join.
Okay, no problem. No problem. I'm just trying to see if my screen share works.
Yeah.
I will try to share my screen and just give me a feedback if it's working fine.
Yeah,
Yeah. Okay.
it's working.
All right. Great. Fine. So I'll stop now and maybe share once we get started. Yeah.
Mom, shall we start? TTM Mom?
Yes, Manisha, you can start.
Yes, Mom.
Okay. Vinod, good morning.
Hey, good morning. How are you?
How are you, Vinod?
I'm good, thanks.
Okay.
It's been a while. Yeah.
Yeah. Thank you so much for accepting the invitation.
No problem.
Okay. Yeah, Manisha, you can proceed.
Very good morning to everyone present in this virtual conference. Welcome you all for the third day of International Conference on Computational Intelligence and Data Science, ICCIDS 2022. So I would like to start the session with the famous quote by Marie Curie on research. Nothing in life is to be feared, it is only to be understood. Now is the time to understand more so that we may fear less. So we will start with the keynote talk by Dr. Vinod Patangai, Distinguished Member of Technical Staff, Senior Member Wipro. The topic of the session is From Features to Embedding, Unified View of ML Pipelines for Text, Audio and Image Understanding. Now I request our conference chair, Dr. R. Priyadarshini, to introduce the keynote speaker.
Thank you, Lokeshwari. Good morning, everyone. It's a great pleasure for me to introduce our speaker for today's first keynote session by Dr. Vinod Patangai on the topic From Features to Embeddings, Unified View of ML Pipelines for Text, Audio, and Image Understanding. Dr. Vinod is a technology leader with 16 years of experience in development of AI and ML-based solutions for automotive, transportation, healthcare, and retail industries. He has developed innovation roadmaps, enabled deployment and production for multiple use cases that help saving time and improved accuracy of workflows. As an inventor, he has filed 25 patents, of which 18 are granted. He has also authored 15 peer-reviewed publications on different applications of machine learning. He is currently with Wipro as a distinguished member of technical staff as a senior member. Thank you for accepting our invitation, sir. We are very happy to have you here with us for our international conference, ICCIDS 2022, as a keynote speaker. We welcome you once again, sir. Over to you.
Thank you, Priyadarshini, for the kind introduction. And it's great to be here. It's nice to interact with in a conference where the people are very focused on to one particular area. So that's a reason why I chose this topic. Okay, can I share my screen? I think I don't have permissions to share.
Permission, screen share to the permission.
I guess whoever is sharing now has to unshare.
So we will look into that.
All right, no problem. So that's okay. By the time we fix that, so can I have a raise of hand on how many of you are faculty and students and at least how many of you are students? Because I see around 51 participants. So I just want to get a sense of how I can, fine tune the lecture in a way that it's more accessible. So the way I've done this is, so this talk is not expert level. This talk is more like somewhere between beginners and intermediate level, right? So I just want to understand a little bit from you in terms of, maybe through the talk, and what is the sense that all of you have in this area. And this is a very important area, and I'm glad this conference is taking place in the first place. Okay, so let me try sharing screen. Yes, I can. Thank you. All right, let's make this full screen. Yep. So over the past few years, I've been interacting with a lot of people who want to work on this area and also who've been working in this area for quite some time. And I realized two things. Okay, one is uh, the new set of people who just started working in machine learning, deep learning areas in the past few years, let's say 2 to 3 years at most, and they have started off when the advancements in deep learning have already matured quite a lot. So their understanding is mostly in terms of using a pre-trained model and being able to adapt it to certain use case or certain applications that or certain problems that they're trying to solve. So that is one set of people, and the other set of people which I've interacted with, which I also belong to, is uh, people who've been doing this for a long time. Like I started working on this in during my masters, and this way back in the early 2000s. So, and when we started working, there was no deep learning and there was no embeddings. Uh, in fact, there was no cloud, and we had to really struggle for compute. And but at the same and there was lack of data to train big models. So we used to spend a lot of time trying to create or handcrafted features. So this features would have to um, contain a lot of domain specific information. So that means whoever is building features will have to be very good at understanding the data, understanding what domain the data is from. Is it speech, or is it image, or is it text? And the techniques are very varied. Okay, and so what I realized is there is uh, a gap in continuity between people who work only on features to start with and those who've just started working now, like this year or the past 2 years, students who just graduated, or people who started working on this when they changed from another area, for example, right? So their understanding, because those are the set of people or researchers who have a very strong understanding of embedding, but they don't actually have any knowledge or experience with what features are. So that is a connect that the first the bridge is what I want to establish in this talk. Okay, and second thing is I've also noticed a lot of people who say that, hey, I'm a NLP expert, or I'm a speech expert, or I just do a computer vision image processing expert, right? But then I'm in the industry, or it doesn't matter if even if you're in the uh, academia, or even as a researcher, right, as a master's student or a PhD student. So sometimes the problems come to us in different settings. So if I'm doing audio or speech processing, uh, can I adapt and do any kind of time series data? Can I do stock market prediction? Can I do oil price prediction? Or can I do even things like COVID spread prediction? Right? So these are different problems. The data sets are different, but if you really think a little deeper in this, the pipeline or the algorithms that are used are very similar in all these problems that I mentioned. So that's the reason why I thought there's another um, understanding that is which I realized based on my interaction with people in the community, is that there is no unified view of ML pipeline. So I'm using the word pipeline because uh, it's we can think of any problem solution as a sequence of modules, which is where data flows from one module to another module. So it's like a pipeline, right? So it's just a flow of data and control. So that's a reason why I use the word pipeline. And that's a very fairly commonly used word. And there are also phrases you will hear: data pipeline, which is an expansion of the ML pipeline. So usually it's a data pipeline or a workflow uh, where data comes in some form, like text or images, and then it gets stored and then it gets processed. Then somewhere there is some dashboarding happening. So eventually the ML pipeline takes care of the processing of or inferencing of the data that comes in, and it's a subset of the entire pipeline in the whole workflow. So that is what I was trying to say is the unified view of ML pipelines for different problem statements or different problem domains with text, audio, and image understanding. I think there is the lack of this view in the community, and those are the two reasons why I thought I'll merge these two issues and then put together in a talk and share it with you all. Okay, so we'll get started off with. Oh yeah, by the way, I just want to also mention I'm assuming a beginner to intermediate level audience. So uh, uh, if you have some questions or something, and you could hold on to it. And I don't have a lot of material because I just want to make sure I cover the basics, and it's more of a way of visualizing the pipeline rather than any specific in details. And I'm not getting into a lot of details, but the intent is not to leave out details, but intent is to see at a higher level how things are common. Yeah. So good. So let's get started. I think I've got around 20 slides or so, and I plan to do it take about half an hour, and the rest of the time we can have a Q&A. Okay. So we want to know what is a feature, right? So feature is how we represent data. If you have images, you want to represent it as a feature vector, which is essentially a row vector or a column vector. So if I have, let's say, one sentence, I want to represent a sentence with a vector. Okay, so suppose if I have 100,000 sentences or 100,000 images, so the vector gets stacked and it forms a data matrix or a feature matrix, if you want to call it that way. Now, what you're seeing here is I'm just showing you in 2 dimensions. Okay. Now suppose the dimension of the feature is 2, so I can plot it on a 2D screen. What you see in the bottom right. So there are 2 classes. Is gray and is blue, and a good feature. Let's not worry how you got this feature. You could get it from text or audio or an image, and you could see that ideally what you want features to be nicely clustered, so your classification accuracy is good. Okay, so which means you don't want the features to merge too much, but you want them to be separated. Okay, and you also want them to have a low intra-class variation. So that means they all group together form nice clusters, but in reality it doesn't happen because there are always corner cases. There are always some samples which tend to be in between 2 classes. Okay, and also you want the feature to give you a high inter-class variation. So that means an extractor feature, it should not be 2 different classes or too close together, but they have to be far apart. And there are some other non-functional requirements, if I can call it that way. They got to be fast. You don't want it to be taking up a lot of memory for storage and processing, and you want it to be insensitive to noise. So that means if my signal is corrupted by noise, the feature still holds good. Or if there's noise in the image, then it doesn't mean that it gets misclassified, right? So then this is a new thing, which is actually gaining a little popularity now. It's called multitask representation. You don't want the feature to be different for different tasks. So for example, if I have text, then I could do intent extraction or sentiment classification, but you want to use the same feature for both. So I'm very efficient if I have a pipeline which uses the same feature for multiple tasks. So that's the idea in the feature. Okay. So there are some examples I just collated for let's see, yeah, for text or for natural language. Well, some of you have been working in this area probably know this. For if you've been working on it for a long time, you could use what is called as one hot encoding, which means that every word, if I have a language which is having, say, I'm just saying 1,000, in English it's a lot more than that. So I represent a sentence with as a binary feature vector, and which says if the word is present, it's 1. If the word is absent, it's 0. So it's like one hot encoding. Then an extension of that, if 2 words are present or if n words are present in a together, then you call it an n-gram. You can start off with 2 grams, 3 bigram, trigram, and so on. So it takes into consideration co-occurrences of words. And bag of words again is an extension of that. And TF-IDF is term frequency, inverse document frequency, and so on. So there's a lot of material on this. And if you're an NLP person, you've been working on it for 5-6 years, then you might have started off with these, right? And the same way for audio. When I used to work 20 years back, and it used to be frequency domain features, Mel frequency, linear prediction. There's something called Forman frequencies, and zero crossing rate also used to be a pretty popular feature. Then people used 1D wavelets for speech. Uh, in image, again, some of the popular features are HOGs, histogram of gradients, and even you have visual bag of words, and LBP used to be popular about 10 years back. Local binary patterns and wavelets again used to be popular. So if you see literature today, it's very hard to find these things. Although I'm not saying this, we have to rule this out. And these are very fundamental concepts. A lot of people spend time understanding text, understanding audio, speech, images, and they came up with these features. And they built pipelines where the starting state in that pipeline or block in that pipeline actually had these algorithms in place. Yeah, and then so this is how a pipeline used to be built in a traditional sense, and there's nothing wrong with this. It still solves many problems today, and in sometimes these are the most efficient pipelines ever built. Okay, because it's very nicely handcrafted to a particular type of data that is coming in, if it's words or audio or pixel data, and we do a feature extraction, then we get the column vector, row vector I was talking about, and then you have a classifier um, which again, there are quite a few choices, or at least there used to be quite a few choices. And neural networks, support vector machine, random forest, and there are a lot of others which are not mentioned here, but they're by themselves good algorithms to use. And and once your classifier gives an output, you do some decision, you threshold, or you sample aggregate, rate limit. If it's time series data, you're taking time windows, and you have a decision module that aggregates different outputs for different time windows, and then you can do that. I'll talk about a few real world applications towards the end of the talk. So this used to work great till about 10 years back, where things changed. Okay, now I'll just flip slides back and forth. Okay, so this was a traditional pipeline, and now if you see current state of the art, this is how we have started doing it this way, right? So now what happened is we've tried to build an end-to-end deep neural network, which has different layers. Let's not worry about what the layers do right now, but there are layers that act like feature extraction, the layers that act like classification or detection layers. And now there's a lot of work done on how you can design these layers, how many layers. Oh, by the way, I should also mention that as a for starters here, that the word deep uh, actually means that if you have a neural network with more than 3 layers, then you call it deep neural networks. Now 15 years back, we've been working on neural networks which are 12 layers or 15 layers, and we never use the word deep. But in today, there are models which have 128 layers and 50 layers, 60 layers, and so on. So which actually take weeks to train. Okay, even on multi GPU clusters and so on. So they are very deep neural networks, and that's when it got more and more popular. So the idea is now the training algorithm that you use to train a network takes care of optimizing the feature extraction, takes care of optimizing the classification, and I don't have to worry about it. Whereas in the past, like suppose if I have to worry about, say, if I want to extract a feature in images, I have to worry about if I'm going to use histogram of gradients, I have to worry about how many histograms, what will be the bins in the histograms, what is the gradient bins, and the same way, if I'm going to use binary patterns, local binary patterns, how many directions I have to use. So there are a lot of parameters at the feature level and also at the classifier level. But now I don't worry about it, but I let the training algorithm take care of all the parameter optimization. In fact, I don't optimize anything. So I'm done with handcrafting features because I don't have to worry about how many bins in the histogram. I'm done with setting SVM parameters or SVM thresholds, and a new value, C value, and so on, because the gradient descent or atom optimizer will take care of, I know at a holistic level, uh, based on the training data you give, all these, the weights are optimized to minimize the cost for the training and validation data, training data at least. So that gave a lot of comfort, right? So, but there's a trade-off. Now, these neural networks are quite dense, quite uh, have many layers. So the computation time required went up, right? And it's not easy. If I have to, and I can't train these at home on my laptop, and I have to run it on a cloud instance, or I need to set up a cluster in my lab. So which is going to cost some money, and uh, but once it's a one-time thing, right? If I have the budget, if I buy a GPU instance on the cloud, or I set it up in the department or in the lab. So but people can use it for training run different types of experiments and so on. So on the other hand, so these are the advantages I already mentioned. So, and the most important advantage is because I don't handcraft anything, I don't do, as a human, I don't change any threshold or change any parameter in different stages in the algorithm. The training algorithm optimizes everything for me. So the accuracy, what we have seen in fact, a lot of benchmarks out there, uh, the accuracy in today's state of the art is way higher than the traditional ML pipelines, right? So that is why you would not see anybody talking about traditional pipelines today. And even if they are in production in some industries, um, there's a specific type of data, it's working, they don't want to change it because it's already giving you what the kind of accuracy you need. But only in certain scenarios like that, people still maintain it. But if I'm building something from scratch, I would always not use a traditional pipeline, but I'll go for a pipeline which looks more easy to train and easy to optimize parameter wise. Okay. So now the question is, you have to train all the layers from scratch. Okay. Well, I did mention there are some networks which are which are 128 layers and so on. But if I have trained it on my laptop, it would take me a few weeks just to train them. Okay. So the answer is no. I don't have to train, but I just have to get a pre-trained network from someone else. Now, somebody else might have the resources, the data to train it, and somebody else wants to popularize their brand or their contribution to research, right? And so they're giving away this pre-trained model for free, and so that helps them in certain objectives, but it also helps us uh, in our objective to solve a particular problem, right? So and without having to train and spend a lot of effort training. So that's why if I use a pre-trained network and just use the embeddings, then my problem is way easier than what it used to be. Okay, so let's go back and define what an embedding is, right? So now this is how we. I did show you one of the previous slides that this is a big or a or a deep, I mean, multiple layer network, but you can split it into two parts. Right? One is you have a pre-trained network and which is giving output at some level, and then I have another smaller network which I'm appending to that stack of layers, and this output of the pre-trained model is what we call the embedding layer, right? Embedding, or it's also called a deep feature these days. Now, if I'm a beginner, I will just say, okay, hey, I have a problem to solve. Maybe I'm doing course assignment, or I have a problem and I have to solve for a customer at my job. Uh, so I don't want to train the whole stack of layers, right? I just want to see, okay, what is the best pre-trained model which I can select from the community, right? Community meaning open source, and also assume that the licensing and everything is taken care of. So I don't. I mean, if I'm a student, I won't really care about it, but if I'm using it commercially, then I just have to make sure it's not violating any commercial rights. So that is a minor thing, right? But most models today which are available, they don't put any restriction on how you can use it commercially. So we've built many applications or of such kind where we've used pre-trained networks and we've fine-tuned them, and we've added more layers and trained it for specific tasks, and it has worked quite well, and we were able to turn around and deploy solutions in way less time than we would have taken if you had to build everything from scratch. Yeah, so so the key is you got to use embedding for downstream tasks. Now, downstream tasks, I will explain what few downstream tasks are as we go forward for different domains. And now, suppose what happens when a pre-trained model is not available. Okay, let's say I'm doing COVID prediction, or COVID spread prediction, or say stock prediction or oil price prediction. Now, I will not most likely get a pre-trained model for that, because pre-trained models are available for very common use cases in text or image or audio. But sometimes we will have to think and see, look, I have lots of data coming in, but I can still create a pre-trained network and use it for prediction or classification and create my own embedding. And that I can only do if I have enough data, and not just the quantity but also the quality. Yeah, and then I have to evaluate the embedding for multiple downstream tasks, right? If embedding only useful for one task, it's not very useful, right? It gets tightly coupled to that task. But if I say, I can use it, let's say text data, there's a text embedding called BERT, and I'll talk about it in the next slide. I can use it for sentiment, I can use it for intent, Q&A, it's one of the most interesting embeddings that we've been using for the past few years. Yeah, so this is how we use a ML pipeline with a pre-trained model. And now the other question is, okay, how do I create this if I don't have it? So I have to create it. So how do I create it? Now, if you've been reading some literature, you would have heard the word autoencoder. And what this does is, when we feed an input data, we try to encode into an embedding, which sometimes it is a very small dimension layer, but it does not have to be. And then we pass it to a decoder network, which basically mirrors all the operations. I mean, at least the layer wise. And again, it does not have to be, but I've seen most papers actually try to mirror it. So there's an encoder half and a decoder half. And when you train it to minimize the reconstruction error. So if I'm giving an input vector, I want the network to learn how to generate the same output. And it might sound very counterintuitive. It might sound to you like, hey, why do you have to generate an input or generate an output which is the same as the input? Because if I have the input, what's the point in having output which is the same? So the answer is, the output is not important. Output is only important because we want the embedding layer to capture the distribution that is there in the data. Okay. And now suppose my reconstruction error is low. Let's say my input data dimension is 100 and maybe the embedding layer I set it as 50. So that means 50, a vector of 50 numbers is good enough for me to represent a vector of 100. Or sometimes there could be noise in the input layer, but this can filter out the noise, or this can remove the redundancy in the input vector. And there are, just to also mention, there are other linear methods from statistics. There are methods called principal component analysis, linear discriminant analysis, iterative component analysis, and so on, which have been used traditionally for dimensionality reduction from the statistical machine learning approach. But in the neural network approach, the current state of the art is use an autoencoder, use a decoder network, encoder-decoder network, then try to train this so we minimize reconstruction, and then use this as the embedding layer. And what I do is once I do this, I just have to throw off the decoder network, only retain the encoder network, right? So the pre-trained neural network that you actually see is a network that has been trained using an autoencoder. But there are other ways of doing it, but this is just one way of doing or creating a pre-trained model using an autoencoder. Okay, and yeah, and you could create embeddings for text, audio, image, or any kind of data, and we just have to have sufficient training samples. Okay, here's a thumb rule that I follow in all my experiments is that there's a way to create or calculate the number of free parameters in a neural network, right? Let's say you design a large enough network, you easily run into millions of, or at least 10 million free parameters. And the thumb rule is try to get at least 5 to 8 times or even 10 times data samples as there are number of free parameters in the neural network. Okay, so that's when you will get good generalization in the network. So that's when, but there are some cases where you don't have so much of training data, right? So, but if I want to create an embedding or a pre-trained network, that's a thumb rule that people typically follow. And but when I want to use the pre-trained network for another downstream task, or say, if it's text, then it could be sentiment classification or intent extraction, then this can be a smaller network. Sometimes even just one layer is good enough, right? So let's say this embedding layer is 100 and I want to do a 2-class classification. So this can just be two node layer, that's good enough, because all I need to do is train the weights from this 100 is to 2. 100 to 2 weights, I need to train 100 to 2 weights, right? So we've seen in some applications that actually works quite well. So I did talk about how you can create your own embeddings, and then we'll get into some pipelines for different domains. Let's start with text. Now, I want to mention BERT here because over the last 2 years, the kind of accuracies people have started getting in NLP applications, when they're using a model like BERT, it has really jumped many times. So the pipeline would look like this. You have a sentence, you encode it. Of course, you can't directly give a text, a string to the neural network. So you need to encode it into something like a numeric vector. There are ways to encode this. There are multiple ways. A simple way could be, so if say there's a sentence which has say 10 words, and you want to represent each word with one number, and the number can just be a lookup table for all the words in that corpus, all the unique words, or all the unique words in that language. It's English or Hindi or Tamil or Kannada or whatever. So you can have so for every sentence I have a sequence of numbers, right? So now I put a limit and say, I can only process in batches of 25 words. So if my sentence is say 10 words, the rest of them are all 0. My sentence is just 20 words, the rest 5 are 0. If my sentence is, usually sentence is not beyond 25 or 30 words, unless there are some legal documents which have a lot of clauses, right? So if I have a vector of text encodings, then I could use a pre-trained model to come up with an embedding. And in fact, the BERT gives you an embedding in 768 dimensions. And then you could use that as a deep feature to train your own network. In fact, you could even, if you don't want to use a neural network here, you could even use an SVM, because it really doesn't matter. It's just a classifier. So you could use it to downstream for different downstream tasks, intent, sentiment, compliance. I'll talk about this one. There's one real world use case which I want to show you. And sequence to sequence, essentially, this is use cases like translation, right? So if I have English text, can I generate another language output, which is fairly complex, because again that needs not just embedding, but it also needs generation of the language. So I'm not covering that in this talk, but that also uses the embedding layer to build on top of. Okay, and BERT is just one model. There are a lot of variants of BERT which has come out, and there's also a Indian language BERT model. There are also people working on models which have mixed code text. So if you see Twitter text or some social media text, then you don't have people only using. They use English words to represent local language words, right? So the text is not in other language, but the text is in English, but it means something in a different language, right? So those are things that this model cannot handle. So I've seen people who, there's some researchers who are trying to address that problem. Because most of the tweets or my short messages don't actually have perfect English or perfect language at least in our Indian context, they don't have always English, and they'll have some other language mixed in it. Right? So that's an interesting use case. So now let's also look at other domains, say images. Now the interesting thing is this whole concept of using embedding, it's called this transfer learning. This actually started off in images, and it's been popular in image computer vision community, image understanding community for over 10 years. And this concept got pushed into the text community. That's when the BERT model came out, and in the last 2 years. So transfer learning and the notion of using pre-trained model is not very new. It's just that the text people who use doing text have just started using it in the last 2 years. But in the image, it's been there for quite some time. So again, if I want to do an ML pipeline for images using pre-trained embeddings, there are a lot of pre-trained models available for images. In fact, you could start off with VGG, ResNet, Inception, YOLO, MobileNet. There are models for image classification. There are models for object detection, which is slightly more complicated, more sophisticated. And you could train it for different types of images, and you could do let's say these tasks are even if you don't want to do some other kinds of tasks, but at least image classification object detection tasks are fairly easy workflows today, right? There are very nicely written tutorials, and even if you don't have a lot of research background, you could just fine tune a model for your use case. I will show you one real world example of this down the next few slides. And after images, there's also audio, right? So again, in the pre-trained model, trainable layers, use it for classifying audio category, music or speech classification, or different types of music, or then there's one use case where I've worked on to identify a certain type of noise coming from a vehicle. Okay, if that there is a problem with the engine, then it generates a certain type of sound. If the engine is okay, it generates a different kind of sound. So those are some examples. Now the interesting thing in this YAMNet model, which is used in audio, this is again from one of the very popular libraries. What the workflow is, they convert audio to a 2D image, okay, which is what people call spectrogram in audio or in speech. So it's basically taking the audio signal and doing a Fourier transform, and then you take the windows of audio and then put the Fourier transform. Fourier transform gives you a complex number, so you take only the magnitude of that and then put it as vectors. And I should have put an example of this, but the idea is not to get too deep into the pre-processing of the data, but the idea is to show you that even if it's a one-dimension data, it's like audio or speech, you convert it into 2D, right? Then process it like the way you process an image. Now that's an interesting method to do it. So there has convolution layers and an embedding layer. Then you could use a downstream classification layer to do the kind of tasks you want to do, right? So there are other popular embeddings, VGG-ish, then Wave2Vec again, mainly for speech recognition that's being used. Yeah, and so now let's go back and see what do we want from, how do I say what a good feature is or good embedding is right now? We're no longer talking just features, we're talking embeddings. Now for the newcomers who have started working in this, they don't even care to understand the difference between a feature and embedding, right? Because I don't care, if it works the way it is, and why should I go back and learn how things were done in the past, right? There's nothing wrong with that, but you need, it's nice to know why you're doing what you're doing. Why did I come all the way to use BERT model today after all the research that has been done in the past 20-30 years, right? So this talk is about trying to answer that question. Okay, and so coming back to what a good embedding is, we want everything that is there in a good feature, yeah, but let's not bring in fast to compute, because embeddings are, if you think deep neural networks, I know the BERT embeddings like 100+ layers, so it's really not that fast to compute. So And the advantage is, okay, you get a good representation of the distribution of the data, and you can adapt it to new data. And now suppose the data has changed, the season has changed, or maybe if the camera data and the sensor is deteriorated in some way, and there's something called the model drift. The data has moved away from what the model has been trained for. So I need to retrain it. So, but I don't have, the data has changed only recently, so I don't have a lot of data to retrain it fully. So I just have to do a small model update or model fine tuning. And that's one of the advantages of using neural networks. You could train it in batches, and you don't have to do a complete retraining, right? And unlike other types of classifiers, where you don't have, although there are iterative optimization loops in the training algorithm, but it's not very easy to go back and say, I have new data sets, so let's retrain it. And a good embedding will also give you the learnability for different downstream tasks. Okay, so that's what I mean by this is the feature vector you get out of the embedding is going to be helping you solve a lot of problems. Let's say here, it helped me to solve different sentiment or intent, compliance, and so on. So examples like this. Okay, so okay, this is also important. Just do a time check. Yeah, it's almost 9:50. So when not to use embeddings, don't mess with something which is already giving you desired accuracy, right? So some industrial applications you don't want to change just because it's cool to use deep learning. Doesn't mean you always have to use it, right? Especially in embedded, low power, low memory. Some of these pre-trained models I talked about are 500 MB plus, right? So it's really hard to get memory if it's an automotive or if it's an edge computing type of use case. And I've seen people use embeddings, on one type of, which are trained on, say, one type of images, then use it on, say, IR image or X-ray image. It might give you some accuracy, but I really doubt why it should work. Okay, so let me interest of time. Let me just talk about two applications. I just want to introduce the problem a little bit. Okay, let's say you order something on your food ordering app and then it doesn't come. Then there's a chat that you have, and then you keep saying, look, you ordered, you pay the money, but it does not come. And the other end, somebody else is responding to your chat saying, okay, we try to fix it. Are you happy with our service? Or maybe they say, okay, we'll give you a refund. Then you say, okay, fine, I'll take a refund. Now, let's say hundreds or thousands of these conversations have been accumulated, and I want to find out how many of these 1,000 conversations or 100 conversations are actually the person who has ordered and is satisfied at the end of that chat, right? So if I'm saying, okay, are you happy with our service? The user says, no, I'm not. I really think it's a better service I deserve. Or I'll say, yeah, I'm happy with the service. So this is if I want to map it as a two-class problem, let's call this a resolution classifier. Okay, and all you need is the chat text, extract embeddings out of it, and build a two-class classifier which says, okay, problem is resolved, problem is not resolved, right? And then use that classifier again. Same, this is the training workflow, the testing workflow, the inference flow, and then you are able to decide out of those 1,000, or even if there are 1,000, maybe in a month you accumulate 100,000, 300, a million conversations that are there, and you can assess how many of these conversations actually gone well. So this gives you a very easy workflow to make this decision. It's very useful for a business to know our customers happy with the service or not. Okay, and move on to another one. So we all may, at least before COVID, used to go and buy things in a retail shop, right? So but you want to know what is actually kept on the rack, right? So you want to detect objects. It's just object, and maybe there's some tweaks to it. So how do we do it? We just take a pre-trained model and train it for certain types of objects, generate an updated model, and use that model in inference. A lot of pre-trained models available. FastR is CNN, YOLO, SSD, RetinaNet. Object detection is a complex problem, but the nice thing is it's been solved many times in many researchers, and then the state of the art is quite mature. So you could start off with something which is quite mature already and fine tune it for what you want. So I'll show you one result. These are some this is from our lab where you have different types of objects and they were trained, and you can see that they've been identified correctly. And also this codes out here basically to say, this is shelf 1 or shelf 2 and so on. Yeah, so I think let's conclude. So I want to point out the similarity in ML pipelines used for and that use pre-trained models in text, image, and audio time series types of problems. So if you're good at text, it doesn't mean you can't do problems with image. Doesn't mean you can't solve the audio data problem. So then, this is what I think will happen going forward. This is my opinion, is that going forward we'll not go around saying, hey, this guy is, this person is an NLP expert, or this person is an audio or speech expert, person is a computer vision expert. You say, this person has this person knows how to build uh, data science or ML applications. Doesn't matter what domain the data is coming from. You identify the use case and build a pipeline for it. Okay, that is one skill. The other skill is, okay, one more advanced level is, okay, even if the pre-trained model is not there for that domain, the skill is to person will be able to collect enough data and create new pre-trained models for that. Right. So that using transfer learning. Right. So that's my conclusion, and I have some future directions. I think we just have, it's already 10. I'll quickly walk through it. There are not enough models for which are localized, right? There's not much work done on, say, Indian language translation, or not just language, but you'd also do something like speech translation. Right? This was a dream problem of my professor too. He used to say, if I'm calling up somebody and I speak in English, and the other person has to be able to hear in language of his choice or her choice. Right? This problem, it is not really solved, and I think this really deserves a lot of attention. Okay, and it's good to identify data-rich problems, because we have to start with data, and today the data is like you can only think of building solutions. You have 100K samples to 1 billion samples. Right? So previously people used to try building solutions 100 samples and 1,000 samples. That's really not going to happen anymore, right? And then there is also a gap which I noticed is that there is no community pool for training large models, right? So if you see cryptocurrency mining pools, and they're very successful in cryptocurrency mining, and they're able to pool in resources, and people contribute their compute power, whatever they have. They don't, even if they don't rely too much on the cloud, because cloud works out to be expensive. But so can we emulate that community model to contribute computing pool to train large training models, right? So you could do things like federated learning, where the models are trained at the level where the user is collecting data. Okay, and that's again open area, and not many solutions available for that. And what about using the mobile CPU and GPU? In fact, today most of the smartphones that we have are as capable as a laptop in terms of computing power. But it's, if you really see the idle all the time, right? So if I have a community model, can I use that compute power and contribute it to, at least among researchers, we want to share compute power, right? So that's another gap which I don't really see today. So I'll pause now, and if there are any questions, and open it up. Yeah. If there's time.
Vinod, I have a question.
Yes.
Can you just give little more light on how to reduce dependency on cloud? What do you mean by that?
Okay. See, now if I have to train a model, right? The easiest way for me to train a model is we buy an or it's not exactly that you buy, but you spend money and you get an instance, a GPU instance or managed GPU instance on any of the cloud providers. Sorry?
No, Vinod, proceed.
Yeah, so that's the easiest way to do it today, because I don't want to be spending wasting time trying to train a model on my laptop or a desktop at home. It's going to take too long. I might have power cuts at home. So eventually it's going to be done on the cloud, right? But then how do you avoid dependency on the cloud is something we have to see, right? So my idea is, if we can create a pool of resources, there are a lot of distributed computing frameworks available where I think there's something called recently there were quite a few frameworks coming out. I was surveying a few providers. I think even Intel has come up with something. So you could distribute it among different devices that you have. So you could do it. I mean, maybe in your lab you have, say, 5 or 10 desktops, and maybe there are some smartphones people want to contribute their computing resource to a common cause, right? So there are ways to do it, and it's still not very mature. I'm saying it's that's why I put in future direction, because we have to mature this as a community. So that is when we can reduce the dependency on cloud. Otherwise, today, if I don't have cloud credits, if I don't have money for cloud, then I have to stop my research.
Yeah.
Right. So that's how it has become. We're so handicapped without it.
Yes. Even in academia, most of the student projects are right now with Coda.
Yes.
That sort of environment only we are preferring ecosystem. So you mean to avoid that, and we need to have an infrastructure within our facility that will be good. That's what you are claiming, right?
Yes. And this is already done in another setting, right? Let's say this cryptocurrency mining, people have that community, they've already solved that problem. They are not depending on cloud.
Okay. Thank you, Vinod.
Yeah.
Thank you. I think there is a question in the chat as well.
Okay.
Dr. Bettina has put some
hold on, let me just take a look at it.
When we talk about fine-tuning part,
Yeah.
what are we actually doing? Does changing parameters of the model apply as fine-tuning?
Can you repeat that? I couldn't hear you.
When we talk about fine-tuning BERT, what are we actually doing? Does changing parameters of the model apply as fine-tuning?
Yes, it does. It does apply as fine-tuning, because there are two things you could do, right? One is you could update the models of the pre-trained model that you got. That is fine-tuning, or you could have additional layers after the pre-trained model. That is what people call it as transfer learning, and people tend to do both actually for good results. If you want to see, you could vary learning rate and all that, and there's there's no exact answer for this, right? It's all empirical, so you got to try out different things and something will work. I mean, even after 15-20 years of research, unfortunately, this is how it works. Because there's no theoretical way of saying that if I fine tune it this way, then that is the best way. No, let the algorithm decide, let the training algorithm decide what is best.
Yes, we do have a huge lot of problem there. That is going infinitely, no? When we start keeping one parameter constant, keep on changing others, and how long we will try that for optimal result.
That exactly was the point, ma'am, because
Yeah,
we keep
that's what,
changing the parameters,
yeah.
but then nothing happens. But suddenly out of nowhere,
Yeah.
just a small change would make a difference.
Yeah.
So,
Is it anything to have some idea about based on the problem statement or data distribution? This is the range of values for these parameters sort of thing. At least for how many epochs we need to do. This is a large problem, right?
Yes, yes.
And we are
This
not
is,
comfortable
everybody is
with
facing
that.
problem.
That is a research also, right?
Yes.
Yeah. Yes. Yes. Thank you, Vinod. Is there any other question?
Okay, thanks. I hope this was useful to you all. And thank you again.
Manisha, if there is no question, you can proceed.
Thank you, sir, for your insightful talk on understanding ML pipelines for text, audio, and images. Your talk gave us an idea about what are the good features in NLP, audio, speech, and images. And we also understood the difference between ML and DL pipelines, autoencoders for embedding and also decoders, similarity in ML pipelines with pre-trained models, transfer learning, BERT, and applying these models for the two real world problems such as problem resolution in text and retail object detection. Finally, you gave us an overview about what are the open research areas in this field. Hope the participants would have taken about the insights about this different technologies and different models available. Thank you very much, sir.
Thank you.
I thank all the participants and I request the participants to fill the attendance as well as feedback for this session, which was shared in the chat box. Now the next session, we will have paper presentation as 2 parallel tracks. In track 2, there will be like 10 papers, and in track 3, 10 papers. Please join the corresponding Zoom links for the paper presentation sessions, and we will have the next keynote talk at 1:30 p.m. Indian Standard Time. I also request all the participants to join virtually for the keynote talk at 1:30 p.m. Thank you, everyone.